Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are looking at Newton's third law of motion. Simply put, we always said in the past that Newton's third law can be stated that for every action there is an equal but opposite reaction. But looking at the definition that I've given you here, if body A exerts a force on body B, then body B exerts a force of equal magnitude on body A, but in the opposite direction. Now, let's take a specific example. We have table, got a table, and on the table we've got a book. Then we have to identify the forces that are acting onto the book. So then we see that the book applies a force on the table. And we can say that the table applies an equal but opposite force onto the book. So we can say book applies a force on the table. And then the table applies a force on the book. Now what's important in Newton 3 is that we must remember that we are working with two objects. The two forces are not acting on the same object. In Newton 2, for example, we see that there is a trolley and you are pulling the trolley front with an applied force, and friction is applied on the trolley, pulling it back. So applied force is on the trolley, and the frictional force is also on the trolley. So in Newton 2, we are speaking about one object, and in Newton 3 we are speaking about two objects. We could also say in this case here that the earth is pulling the book down and the book is pulling the earth up, and that will also be the two objects that are acting, and we call them action-reaction pairs. We can ask a question here, why doesn't the book move? We can say because there's an object. If you look at the object, we can say that the earth pulls the book down, but the table pushes the book up. And now we're talking about the earth pulling the book. So we got the book here, and the earth pulls the book down, and the table pulls the book up. So the object, the book doesn't move because these two forces are equal and they are applied on one object. That will be more related to Newton 2. Just remember that we must refer to two objects when applying Newton's third law of motion. Now when you're shooting a gun, we have a bullet in the gun. Then the forward force of the rifle, that is the exploding gases in the bullet, pushes the bullet forward. It is equal and opposite to the backward force of the bullet, which pushes the rifle backwards. This is what causes the recoil. So the action-reaction pair is gun pushes the bullet front, or the exploding gases pushes the bullet front, and the bullet pushes the gun backwards. So we're referring to two objects. And let's take another example that we have. So here we have an example of Newton 3. As I said earlier, I've taken it from the free science textbooks. I've mentioned it earlier. And I'll just give you the website where you can go and download the textbook, www.fhsst.org. You can get these diagrams from there. Now, taking it further, we see that we have this example here taken from the textbook. Dineo is seated in the passenger seat of a car with the seat belt on. The car suddenly stops and he moves forward until the seat belt stops him. Draw a label force diagram. Identify two action-reaction pairs in this situation. So here we see that if you draw a diagram, we can see they say start by drawing a picture. You will be using arrows to indicate the forces. So make your picture large enough so that the detailed labels can also be added. The picture needs to be accurate but not artistic. Use stickman if you have to. So step 2, take one pair at a time and label them correctly. If there is not enough space on the drawing, then use a key on the side. This key is very important. And it is important to label diagrams correctly in the exam because you will be wasting unnecessarily marks if you don't do it correctly. Right, so here, what are the forces acting on this diagram? Dineo applies brakes suddenly. So what happens, because Dineo applies brakes, according to Newton 1, what will happen? He will continue moving forward. He will continue moving forward according to Newton 1. And what will happen? He applies a force on the seat belt. So Dineo applies a force F1 on the seat belt, which pushes him forward. And then the action-reaction pair will be that because Dineo pushes the seat belt front, the force of the seat belt pushes Dineo backwards. So the action-reaction pair here is force of Dineo on seat belt, and the counter will be the force of the seat belt on Dineo. That is the one action-reaction pair. The other action-reaction pair that we have is the force of Dineo on the seat. So Dineo is pressing downward on the seat, and that is the action. Then the reaction will be the force of the seat on Dineo upwards. So that will be the action-reaction pair that we have here. And if we want to take it a little further, we can even say that we have Newton 2 also in this case. So Newton 1 was described as Dineo will continue moving forward unless a resultant force comes into play. So Dineo, if he was moving at 100 kilometers per hour, would have continued moving 100 kilometers per hour, but luckily he has the seat belt which pushes him in the opposite direction, which brings him to stop. So Newton 1 is applied where he continues moving forward in a straight line unless a net force is applied to him. Newton 3 is applied by the action-reaction forces, as can be seen here. Dineo on seat belt and seat belt on Dineo. Dineo on the seat, bottom of the seat, and bottom of the seat on Dineo upwards. And Newton 2 can also apply because he is moving at 100 kilometers per hour forward, and the seat belt applies a force which causes negative acceleration, which brings him to stop. So we can see that acceleration comes into play where Dineo is moving at 100 kilometers per hour, and there's a force applied on Dineo. So if you draw it as an object here on the side, we can say here is Dineo. He is moving at 100 kilometers per hour in this direction, and because there is a force applied in this direction, we see that that's our net force of the seat belt is equals to ma, which will refer to the mass of Dineo, and then we see that there will be an acceleration, and then we see ultimately the velocity of Dineo will be 0 because luckily he won't get injured in the crash. So that will be Newton 2 applied in this example. We've applied Newton 1, and here we have Newton 3. So we can see all three Newton's laws can apply in the simple diagram of a person applying dead brakes in the car to bring it to stop. So we will stop there, and that will be just the basics relating to Newton's 3 laws of motion. In order for you to master the section, please go over as many past papers as possible in order for you to do well in the exam. Thank you very much for watching.